So in class, we covered two random network models, and while working on the project, you are going to learn at least three more. So now I am going to explain one of them. Is the Barabási-Albert model, is also a very famous model. So so the Erdős-Rényi, the Watt-Strogertz, and the Barabási-Albert are the three very widely cited and very famous random network models. So now the Barabási-Albert model, it has two parameters, n and k. So n is the number of vertices, as always. And k is, I'm going to explain what k is, but you will see that it's not exactly the average degree of a vertex, but it is close to the average degree of a vertex. So 2k is close to the average degree of a vertex. All right, so for example, this is a Barabási-Albert graph when n is 200 and k is 10. And notice that from this plot, you can see, I made the size of vertices proportional to the degree of a vertex. So what you see is that most vertices have very low degree, but there are some that have very high degree. And if you plot the degree distribution, then it is somewhat close to a real social graph. All right, so there is a lot of vertices of low degree, but at the same time, so there are some vertices with very high degree, and the whole distribution is very skewed. So unlike Erdős-Rényi random graph and the Watt-Strogertz random graph, where most vertices have the average degree, but both extremes are rare. So the average degree here is 19. So remember that k was 10 and average degree happens to be 19. Now let me explain how this model works and how it is constructed. So first, in order to construct a Barabási-Albert random graph, we begin with a certain seed. So yeah, by the way, in this graph, k is not 10 anymore. I think it is 5. So in any case, we begin with a seed. What the seed is doesn't really matter. So sometimes the seed is a complete graph. In network X, the default Barabási-Albert graph generator begins with a seed that is an empty graph. So I chose a seed that is an Erdős-Rényi random graph. Yeah, but it doesn't really matter. So as long as you begin with something, and then what you do is you start adding new vertices one by one. Every new vertex is connected to k previously existing vertices. So notice that, and when every new vertex appears, its degree is 5, right? So every new vertex appears with the same degree, and it is connected to k previously existing vertices. But how does it choose which vertices it connects to? It is not at random, but rather when it chooses vertices it connects to previously existing vertices, then the probability that a new vertex is connected to a previously existing vertex is proportional to the degree of that previously existing vertex, right? So which means that the higher the degree of a previously existing vertex, the higher is the chance that it's going to get new vertices that it connects to, but then its degree becomes even higher, and then the chance that it is connected to a new vertex is even bigger, and so on. So this is the so-called preferential attachment. So which means that vertices with high degree, since they get a high chance to be more connected, so they grow faster, and this facilitates creation of several vertices of very high degree, and this generates this highly skewed distribution of vertex degrees.